All right, today we're jumping into a really important one, paper 33, which is basically the capstone for the non-holomorphic fractal series. This paper is a big deal because it takes a whole bunch of findings that seem kind of disconnected and pulls them all together into one really elegant framework.
So here's our game plan. First, we'll look at the puzzle that the previous papers left us with. Then we'll dive into paper 33's two-band solution. We're going to be super clear about what's been proven, what's still a conjecture, and the absolutely amazing numerical evidence that backs it all up. And then we'll look at what's next.
Okay, so before paper 33, the series was uncovering all these fascinating little islands of knowledge. Papers 28 through 32 gave us sharp bounds, weird numerical patterns, but no grand unified map. Think of that like a trail of breadcrumbs. Paper 28 gave us these incredibly sharp bounds for orbits. Then, in paper 30, we got the first hints of two totally different types of behavior, these orbit and Watson bands. By the time we hit paper 32, we had some really solid numerical data showing this bizarre rigidity window where everything just clicked into place in this very specific way. So naturally, the big question hanging in the air was, are these just a bunch of random curiosities, or is there a single, deep structure that explains everything? Well, paper 33 says yes, there is, and here's what it looks like.
Let's get right to the core idea of the paper. It's this beautiful, clean separation of all the system's dynamics into two completely distinct classes. You can almost think of them as two parallel universes of behavior. Okay, so here are our two teams. On one side, you have orbit-type observables. These guys depend on the whole messy, complicated, coupled XY dynamics. You can't simplify them. But on the other side, you have the Watson class, and their behavior is much simpler. It only depends on the one-dimensional Y dynamics. It's a fundamental split in complexity.
So all those complicated orbit-type things, they're forced to live inside what the paper calls the orbit band. It's this super narrow range of exponential growth rates. It's like a strictly enforced speed limit for that entire class of dynamics. Meanwhile, the Watson class stuff, it lives in a completely separate universe, the Watson band, with much, much higher growth rates. It has its own speed limit, and notice there is zero overlap between these two bands. They are totally separate worlds. And this is a really crucial point. We're not talking about physical places. You can't, point to a region of the map and say, this is the Watson band. Nope. These are fundamental speeds. They're the rates at which complexity in the system is allowed to grow. Now, here's where it gets really compelling. This whole two-band picture isn't just a nice story that fits the data. One entire half of it is backed up by rigorous, honest-to-goodness mathematical proof. Must be crystal clear here. What follows is a theorem. It's not a guess, it's not a numerical pattern, it is proven fact. And here it is, Theorem 3.1. This is the bedrock. It guarantees, it proves, that if you have any bounded orbit-type observable, its exponential growth rate must fall inside that orbit band, BORB. That speed limit we talked about, it's the law.
Okay, so we've got one side of the story nailed down. Now let's move to the other side. And here, we have to shift our language very carefully because we're moving from something that is proven to something that is a powerful, evidence-based conjecture.
So, just to be absolutely clear, this next part is a hypothesis. It's not a theorem. Yet. This brings us to conjecture 3.3, which is called Watson band rigidity. Basically, it proposes that all the Watson class kernels are just as disciplined as the orbit-type ones. Their growth rates are rigidly locked inside the Watson band. And maybe most importantly, it says these two bands are completely separate. The Watson class dynamics never cross over and play in the orbit band sandbox. So you might be thinking, if it's not proven, why should I be so excited? Well, the reason this conjecture is so powerful is because the numerical evidence for it is just stunningly consistent. It's frankly beautiful. The authors really did their homework here. They ran a ton of computations, and the data just paints this incredibly clear picture. And by the way, they made the scripts available so anyone can go and reproduce these results for themselves. And this right here, this graph is the smoking gun. What we're seeing are three completely different ways to measure the Y dynamics, the WBA, a Lorentzian proxy, and an alien kernel. And look what happens. At a really high computational depth, they all trace virtually the same path. And they all land squarely inside that gray Watson band, in the exact same window of the parameter epsilon. This is not a coincidence. This is agreement on a profound level. And it gets even better when you look at how stable this is. As they crank up the computational depth, n, that specific window where all 3 kernels agree, shown here in black, it's identical for all of them. You get this incredibly stable repeating staircase pattern. When you see different methods producing the exact same intricate structure, it's a huge clue that you found something deep and universal about the system itself.
You can think of this as a 3-kernel witness. It's like having 3 independent observers describe the exact same, very specific event. It's incredibly compelling evidence for the conjecture. But, and the paper is very disciplined about this, we have to remember it is not a formal proof.
So, let's wrap this up. What's the big takeaway here? Paper 33 does more than just present a new finding. It gives us a whole new lens, a new way of looking at this entire field of dynamics.
Its contribution is huge. It gives us these clean, clear definitions separating orbit type from Watson class. It gives us one half of the picture as solid, proven math. It gives us a precise, testable conjecture for the other half. And in doing all that, it takes years of prior research and organizes it into a single, cohesive, and really elegant framework.
And of course, work like this just opens up even more thrilling questions. The next obvious step is to try and prove the Watson rigidity conjecture. But the bigger and maybe more exciting question is this: are there only 2 bands, or have we just discovered the first 2 elements of a whole new periodic table of dynamics?